So yeah, so the recording is going to be later on the module in case you want to check this later. My idea today is that I get to at least go over some of the questions that are in the practice problems preparation for the exam, and I prepare a document with solutions that I will be posting after this session. So first and anything, I want to start by saying, yeah, so the experience for the exam 2 is going to be fairly similar to what you had in exam 1. It's going to be on WebAssign through HonorLock. So you're going to access the exam via HonorLock Monday around 6 p.m. You're going to have around 90 minutes of exam time. The exam is not meant to last a whole 90 minutes. You should be able to complete it in 1 hour, but you should have the 90 minutes to complete all the questions. It includes, of course, all the materials from sections 8.1, 8.2, which is the last thing in integration, which was arc length and surface area, which are the couple things that you can do by integration. And then after that, everything will be series, and it's covering up to what we covered this week with alternating series and absolute convergency as well. So pretty much includes everything that we've seen so far in series. So I want to start by asking you if you have any questions that I should address first. Do you have any particular topic that you would like me to go first on? And after that, I'll just jump and just go over some of the different questions that I have for the practice. So do we have any questions that I should go through? Yes, no, maybe. Or any comments that you want to make of anything for this exam? Just give me a thumbs up if I just should move to the practice problems. Okay. All right. So I'm gonna go in order with the solutions that I prepared for today. But there are a couple of different approaches that we can take on the questions of the exam. Sorry. So one of them is going to be, for example, on the arc length. There are certain types of questions that you can address. Since I'm not that interested in necessarily giving you our integration at this point, we're past integration. So this is supposed to be something where you already know the integration. So you might get something that it gives you something simple to integrate a substitution tops. But sometimes it's just gonna even ask you a state what the integral for the arc length is going to be, and that's it. So the first question is an example of a full work around the arc length. You have this formula, and this is the formula that you gotta know. You have a particular curve, and that this curve here is defined x in terms of y. And of course, it's moving y between 0 and 4. That's the domain that we want to integrate on the arc length, the length of the curve. And so that's reflected in the integral from 0 to 4 of the square root of 1 plus the derivative of the square. And once that we get that, then the first step, of course, is going to be finding out who the derivative is. And simplifying a bit because we're going to have to square that. In here, notice that for this particular example, we have root. So when we apply the derivative, we get 1/3 times 3/2 of y squared plus 2 to the 1/2 multiplied by 2y. And then simplifying terms, this becomes y times the square root of y squared plus 2. Now, when you multiply that, then you're going to have that this is simply the integral of y to the 4 plus 2y plus 1. And this is actually that you can fall into a binomial square. And once that you fold that binomial square, then you can cancel the root. And that's something that you're trying to achieve multiple times when you're doing this type of arc length. Since we have a root, we either look for a way of get rid of the root, or you're going to have to use a substitution. In here, we just get rid of the root, and then we got a simple integral at the end. We plug between 0 and 4, and that's it, arc length. Remember, arc length should give me a positive number since you're measuring something. And so that's one of the ways that you know that you're doing fine. Now, again, surface area might be something that you can also consider, but it's a very similar exercise to the arc length. So I'm just going to move on to sequences. If anything, I can return later to surface area with one of the questions if you have one for those. Now, for sequences, you got to be very careful because you don't want to confuse sequences with series. The sequences are not sums, are just a certain amount of terms. And then after that, you just take the sum of those terms. For example, here we want to determine for the sequence if it's convergent and divergent. And this is something that we're going to be able to evaluate just with the limit. Or with just using the theorem by saying this is a decreasing or increasing in bounded sequence. And so that's going to be convergent. That's the two different criteria that you can use for convergency of sequences. So I'm going to call it here convergency of sequences. And I'm going to call it CN. Is either number one, limit when n goes to infinity of Cn is a certain number, or number two, Cn is monotone. And monotone means that it's increasing or decreasing. And of course, also that is bounded. So the absolute value is less than a certain constant A, with A being a positive real number. Okay, so these are the two things that you can use to say, well, this is going to be a convergent sequence only. And then in this cases that we have over here, we can just check on that by simplifying. For example, in the first one, we have -1 to the k plus 1, 2k factorial over 2k plus 1 factorial. That looks like a lot of things, but you can simplify this to k plus 1 factorial with the 2k. You can just really see 2k plus 1 factorial as 2k factorial times 2k plus 1. And so when you cancel all the remaining terms, what you're going to have is that this sequence is really just -1 to the k plus 1 over 1 over 2k plus 1. Now, because the limit when k goes to infinity of this is 0, then you can claim that this one is going to be zero. Since this is something that you can bound with the negative and the positive version, you can use the squeeze theorem to prove that this is zero in general. Okay, so this is how to go with this one. Now, for the most part, you're gonna try to go and do those limits, since that's the easiest way that you can go to prove that a sequence is going to be convergent. In this case, although we have this cosine here, we can just make sure that this is going to be something that we can understand. This cosine of n pi really is going to change determining the value of n. Sometimes it's going to be positive, sometimes it's going to be negative. And so what happens is that this cosine of n pi is just another way of writing -1 to the n. Because that's what ends up happening at the end. So once that we have that, then a lot of this is going to be the same, in that if we determine the limits, we can check where it's going. And this is a scenario when we take the limit when it goes to infinity of just the positive part here. We have that this is 4n squared minus over square root of m 9n to the 4 plus 2n 3 plus 5. And then what we do is we divide by n squared, because that's the biggest power that we have in the denominator. N squared can be seen as a square root of n to the 4. And so we can simplify that here. And once that we see the limit is 4/3, then we can see that this is going to be oscillating between positive and negative values that do not approach zero. And so because that happens, then the sequence is going to be divergent. And so notice that although we got a limit, the fact that we have this -1 to the n bouncing around the values is not going to allow the sequence to converge. If this limit will be 0, then it will be okay, because then it will just go to 0. And then we can consider that the oscillation dies out. But in this case, it's just not, it doesn't happen. Now, example number 3 is also one where we can try to figure out if things go to either 0 or infinity. So for example, here we look for what is the biggest power that we can use to divide here. So we can, in the denominator. And so the denominator, the biggest one is 3 to the n. And so we divide by that. And so on the denominator, we're going to get 1 plus 1/3 to the n plus 5/7 to the n. So all these ratios, this rational numbers are less than 1. And when they're less than 1, all those numbers, they go to 0. Okay. So, and that's going to happen on all these scenarios here. On the top, if I divide by 3 to the n, I get 4 times 1/3 to the n plus e/3 to the n. And notice that this e is less than 3, because e is like 2 point something. So it's going to be less than 3. And so all these numbers, they go to 0. And at the end of the day, this is 0. And the sequence is going to be convergent to 0. It will be a different scenario if instead of e, we have pi, because then pi/3, that will be something that is bigger than 1. And this limit will go to infinity. But that's just in the case that instead of e, we change it for pi. Making sense so far, guys? Any question that pops up on sequence? Give me a thumbs up if so far so good. Okay, so that is the big thing with sequences. Now, series is often a little bit more involved. And you got to remember that in series, what we do is we take the sequence, and now we don't consider the terms in isolation, but we actually start adding the terms. And so that's what a series does. And because we can create partial sums, then you can kind of think as a series as like another sequence, as the sequence of partial sums. And what we're really looking for is if that sequence of partial sums converges or not. But sometimes we just gotta pick the series at face value. Question number 3 says here, let's look if this series converges or diverges by using one of the comparison tests. And so you gotta say, well, we're gonna use comparison tests or limit comparison tests. Depending on whatever you wanna use, then it's gonna be much more easier or not. So for example, what would you use here for this series? What do you think you should use? Just tell me on the chat if you want to. Comparison test? And do you have any idea what series can we use? Do you think it's divergent or you think it's convergent, by the way? Just like a glance.
Oh, I'm not really sure. I usually just go first to the comparison test and
Yeah,
try to check that.
sure, but when you're doing comparison tests, one of the things that you gotta have an idea first is if you think that this converges or diverges. Because if you think it converges, then you're gonna use something that is bigger to compare it. And if you have the notion that you think it diverges, then you're gonna use something that is smaller. Do you have an idea? If you don't have the idea, it's fine. I'm gonna give you the notion next. But if you have any idea that you can bounce, I can receive it now. It doesn't matter.
Yeah, not really right now.
Okay, sounds good. Uh, Notice that the trick is for this particular series, you have powers. Powers on the top, powers on the bottom. You wanna check who the biggest power is. So the biggest power on the top is n cube. The biggest power on the bottom is n to the 4. Does that make sense? So if we consider just a series with the top being n cube and the bottom being n to the 4, what is this? Oh, look. It's 1 over n. Is this series convergent or divergent?
Diversion.
It is a divergent series. You see? So just by guesswork, just by taking the biggest power and making a ratio, I find this is looking like a divergent series. So very likely, this is going to be a divergent series. Now, you tell me that you're using comparison tests. Comparison tests might be kind of hard to do here, to be honest with you. But we can certainly try and use it. Now that I know that I can compare with 1 over n, my gut feeling will be, well, I need to try and just show that this series somehow is bigger than that. So um I'm gonna start by doing, well, 2n to the 4 plus n squared, because I want this to be less, then I need to find out something that is bigger than this. Okay. So I'm gonna go with, and this is the problem because I want to have something simple. I'm gonna go with just Let me see. N to the 5, maybe n to the 5 is at some point gonna be bigger than this. And so on the other hand, why is this what I want? Because then I have 1 over n to the 5 is equals 1 over 2n to the 4 plus n squared, right? I want to have this inequality, but now I want to transform this inequality in something different when I use it here. The problem is going to be that I need to get again like an n to the 4 situation here, so this is not looking promising. So I think using comparison tests here is much more harder than what I was expecting. It's gonna be very when you don't have nothing in the numerator, then it's easy. Is much more easier to just use it. But because here I have a lot of things in the numerator, then it's not so easy. Does that make sense?
Yeah.
Okay, so instead, because this is not looking easy, but I already have this idea that this is a series that is good a comparison point, then I'm gonna use limit comparison test instead. Okay, so by limit comparison test, I'm gonna use with this series, 1 over n. And so I'm gonna do limit when n goes to infinity of 3n cubed plus 2n minus 1 over 2n to the 4 plus n squared, and then divided by 1 over n. Now, this limit is what? Then this limit becomes limit when n goes to infinity of 3n to the 4 plus 2n squared minus n over 2n to the 4 plus n squared. Okay? And then this is limit when n goes to infinity, and I'm gonna divide by n to the 4 up and down, since that's the biggest power of the denominator, and I have an infinite limit. I could do either L'Hopital or divide by the biggest power, but here I'm gonna divide by the biggest power because it's the easiest way to go. So this is 2 over 1 over n squared, and here this will be 3 plus 2 over n squared plus minus actually, since I have a minus here. And I'm dividing by n to the 4, so minus 1 over n cubed. Does that make sense so far? Yeah. So notice that this goes to 0, this goes to 0, this goes to 0 when it goes to infinity. This is 3 halves. Now, this, fortunately, then it's a number that is bigger than 1. So I can very easily know that this is going to be convergent. Sorry, this is going to be divergent. Is different from 0, and so I have that because 1 over n, series of 1 over n diverges, then the main series diverges as well. And this is by limit comparison test. Okay. Does this make sense? All right. Now let me go to another question. Oh, or before, notice that here in the solution here, I have that I can actually use the limit comparison test by approaching the powers, like I was mentioning before. And so because this is a limit, if the limit is bigger than one, is one bigger than zero, then a divergence by limit comparison. The direct comparison is still comparing with 3 over 2 to the n. But then we gotta look for that series. And so we kind of gotta claim that this is bigger than this. And then we gotta claim that this is gonna be bigger than this. And so at the end of the day, we divide that out and we get this inequality where this final is bigger than the series 1 over n. And so by direct comparison, we can also prove divergency. But this step is much more complicated than the limit comparison. So I'll say if you can't, always go for limit comparison first. And then if you can't do it by limit comparison, then try with direct comparison. But direct comparison is a much more harder test to use. I'm not saying it's not usable. I'm just saying it's much more harder to use. And when you're doing series, the good part is that you have the opportunity to make a selection on the test that you're doing, at least when you're doing it on paper, right? If you are doing a specific question that actually asks you to find something in a particular way, then you have to use that way. But in this case, you can see that both scenarios lead you to the same answer, and one of them is much more easier to manage. So that's one of the big takeaways from this part here, from this question. Now, we're going to check some more series here, and we're going to determine if this series either convergent or divergent. And if possible, we're going to find the sum. So for example, for the first one, we have a geometric series. We can just write this as minus 1 to the k 4 over e to the k. This is a geometric series with ratio minus 4 over e. This is actually less than minus 1. And so because it's less than minus 1, then this is going to be divergent. The geometric series are convergent when the ratio is between minus 1 and 1, or when the absolute value of the ratio is between 0 and 1. Now, same thing for B. B is just a sum of two geometric series. And so one of them is 4, really. This 2 to the 2 to the k is just hiding the fact that 2 to the 2 is 4. And so you can see this as 4 to the k. And then after that, you can just see this as the sum of 4 over 6 to the k plus minus 3 over 6 to the k. And by properties of the series, this is going to be convergent only if these two series are individually convergent. The good thing is that each of them is. The series of 2/3 to the k is a geometric with a ratio less than 1. You can actually compute what the sum is sum 2. And in the case of minus 1/2 to the k, which is minus 3/6 to the k, same thing. You can actually compute also the sum here, and it's just going to be minus 1 term. So then to find the sum, the general sum, you just got to add those two numbers. It's going to be 2 minus 1/3, and that's just 5 over 3. Okay. For question C, notice that this is a telescopic series. Telescopics are the series that has the difference between the n plus 1 term and the n term. You can kind of see that when you're taking the first number minus the second, and you start eliminating terms, and at the very end, you're just going to have the first term minus the last term. And so here we're going to get that at the very end, the partial sum is going to be minus tangent to the minus 1 of 0 plus tangent to the minus 1 of n plus 1. When you make n goes to infinity, this is tangent to the minus 1 of infinity. And that's just precisely pi half. And tangent to the -1 of 0 is 0, so we don't have to worry about that one. And turns out that the sum, the whole sum, is pi half. Okay, so in this case, this sum here is going to be convergent to pi half. Notice that it's important to remember that not all the time you're going to have access to checking the sum. That's something that is very difficult. You get certain sums like with the geometrics or with the telescopics, or you can make approximation with the integral test, but actually finding the sum is something that you don't all the time will be able to do. Okay. Now let's see one example of that. But we're gonna use the integral test with the series n equals 1 to infinity of n times e to the minus n squared. And we're gonna write a partial sum without necessarily evaluating the expression. And then we're gonna use the estimation of the integral test to find the error bounds of that estimation. So the first thing is that, of course, we want to use the integral test. And so for that, we got to check the conditions. So f of x equals x e to the minus x squared is going to be a positive function, is continuous, and is going to be decreasing on the interval 1 to infinity. One way to prove, by the way, that this is a decreasing function is just by the fact you can argue that you can see this as this function, and so this is decreasing because the bottom dominates the function. Denominator dominates the function. In terms, it grows much more faster than x. Of course, you can always do the derivative. And so with the derivative, it will be e to the x squared minus x e to the x squared times 2x over e to the x squared square. And so the bottom is positive, and so you only got to check the top. But when you're checking here the top, you can factor out e to the x squared. And so with the one below, you can cancel one of this. And here the top is just going to be 1 minus 2x squared, which is clearly a negative term. So at the end, this is 1 minus 2x squared over e to the x squared. And this is clearly negative as a derivative. So this implies that f decreases. For the most part, this is going to be the most surefire way of proving something decreases, but it's not the only one. And there's going to be certain cases, especially what it involves a factorial, that you will not be able to do this because, let's say, a factorial doesn't have a derivative. Okay. Now, once that we get this integral test ready to go, then we do the integral. We get x e to the minus x squared. This is clearly a substitution. We have that u is minus x squared, the u is minus 2x. And so this is going to transform in the integral of e to the u times minus 1/2 du. And so this is minus 1/2 e to the u plus c, or simply minus 1/2 e to the minus x squared plus c. And then at the end, when we're doing the limit when it goes to infinity of this, this is going to provide me with 1/2e. So clearly, because it's a finite value, then it's convergent by the integral test. And we have that the series is convergent as well. Now, to write the 4 partial sum, I just got to write the first 4 members of the sum. So 1 times e to the minus 1, 2 e to the minus 4, 3 e to the minus 9, plus 4 e to the minus 16. Those are the first 4 terms. How much this is, I don't know. And if you are doing it on the exam, you don't have a calculator with you, you don't necessarily have to write a number. You can just plug this in and that'll be enough. Now, in terms of the estimation for the remainder, remember that the remainder is the difference between the end term and the actual sum of the integration. So we will be doing essentially the difference between this and 1/2e, which is wherever it converges. Now, what we're saying is that regardless of that, the error of this is going to be between the n plus 1 to infinity of this, x e to the minus x squared, and between 5 and infinity and between 4 and infinity. So therefore here the error at the 4 level is going to be less than 4 to infinity, and so you're just simply changing the number that you're going to plug in here from what did you have from before. Here you have 1. Now you're changing it for 4, but the procedure is the same. So now you can replace this by t to 4, and then that's going to give me 1/2 e to the 16. And that's the superior bound for this. Making sense so far? Questions? Give me a thumbs up if so far so good. All right, Trevor, any questions? Now, if we go back to the course and just so we can recall a little bit, what are the topics of this exam? You can see that. Let me just open this up for a bit. We have from arc length, area surface of revolutions, the definition of a sequence in a series, integral tests, comparison tests. And so we're missing to go over a couple of elements. We're missing go over an example of alternating series, absolute convergency, and the ratio on the root test. By the way, this week you have a worksheet, and that worksheet you have absolute convergency. I'm going to be posting solutions of that as well. But I didn't do any of those with either the root test or the ratio test. Okay, so I might use now one of these things using that. Now, but let me start first, and this one is going to be in your worksheet as well. This is an alternating series, and if you use the alternating series test, then you're going to be able quickly to say this is a convergent series. And the reason is that the alternating series test is asking me, hey, do you want to have that the sequence Bn is positive, and that sequence is going to 0, and also that you want to check that that is decreasing. And so there's a lot of different ways of showing that it's decreasing. You can use the derivative of the function. You can use the comparison between the an plus 1 and the term an. And so with that, you can show that this is going to be converging by alternating series test. Now, the alternating series test also has an estimation of the sum, because it's alternating between positive and negative, positive and negative, positive and negative. You can always say, well, you're going to get something that is less than the previous term. And the error between the full sum of the series and the partial sum is going to be in that the error Rn is less than the n plus 1 term, which is very simple. So the estimation here for the alternating series says that if you use that, then absolute value of Rn is less than the n plus 1 term, which in this case is 1/n plus 2. So if you want to have a specific error, so you can consider this the error. So if you want to have that the error is less than 0.001, then you gotta consider that 1 over n plus 2 is less than 0.01. And then from there, what you're gonna do is you're gonna find out who that n is. And so in here, 0.01 is just 1 over 100. So that means that n plus 2 gotta be bigger than 100, or n gotta be bigger than 98. So if you choose like 99, you're sure that when you use the first 99 terms to estimate the sum, your error is gonna be around that bound, okay? And this is the same procedure that we do for all the calculation of the errors. Is always, we're gonna get one single term that is gonna give me the way to estimate who n is. And then after that, we simply go for finding out what that particular number is. Now, so this is in terms of alternating series. And alternating series test, I think, is a very easy test to check when you're working with alternating series. Is just prove that it's decreasing, prove that the limit goes to 0, and if you're checking the error is just less than the n plus 1 term. So it's very simple. It's not even like the integral test that you have to do the integral from n plus 1 to infinity and n to infinity, and you got to remember which one is which from or bottom of the bound. This one is very straightforward. Now, over here, we have a bunch of series in number 7. Some of them are going to be alternating and some not. So at this point, I would like to see if you guys have a preference in any of this. If you had any of this series that you thought it was particularly difficult. And so maybe I can address that one. So any candidates here? Trying to give you some interaction so you don't get bored just watching me talk about this. Since for the most part, even in videos on the online classes, that's what you do. So if this is the type of chances that you have to ask me questions, ask me your preferences. We're here in the question 7. What did you think we should do here? Which one of this? I don't have time for all of them. We have like around 15 minutes. We'll leave this available for you in the solutions. But do you want me to just talk about any specific ones?
Bless you. Maybe F.
F? Okay.
Yeah.
Good pick. So F is minus 1 to the n of 3/4 plus log of n over n power to the n. Yeah, that looks very nasty. And so the thing is, because it has this power to the n, then immediately that's gonna make me think that this is a good candidate for a root test. So this one here, and so an using root test, I'll do limit when n goes to infinity of n root of the absolute value of minus 1 to the n, 3/4 plus log of n over n power to the n. So we get a couple things that are good just from using this. And is because we're using root tests, we can kind of check if this is absolutely convergent or not right away. Similar with the ratio test, we can do that too. But this is the fact that it has a power n is what tells me, yeah, I should be using root test so I can get rid of this n. And so now, and also the absolute value is going to help me out get rid of the alternating piece. So this is just going to be next limit when n goes to infinity of 3/4 plus log of n over n. And now, so this limit is from the shape infinity over infinity, because this piece is fine. This is 3/4. But this is going to infinity, this is going to infinity, so I'm going to have to use L'Hopital's rule. And by L'Hopital's rule here, I'm going to get derivative of the top, 1 over n, derivative of the bottom, 1. Of course, the derivative of 3 over 4 is just 0. So that goes away. And so this is just 1 over n, limit of n goes to infinity of 1 over n, and this is 0. Now, because this is 0 and it's less than 1, then we can actually use the root test here and conclude. We know that this is then convergent by root test. Notice that everything is about the choice of the series. If I were to pick ratio tests, this will be a complicated ratio to do. So it will be messy if I use ratio tests here. I could potentially do even alternating series tests, but it's not that good because it's not only that this is convergent by root test, but I can say that it's absolutely convergent, since this is really going with the absolute value and everything. Well, if I just do alternating series tests, it's just gonna give me information about the alternating series. Does that make sense? All right, any other for this one that looks good? Should I just move on? Okay, so I want to make a small mention. One of the series here that is interesting will be h. This 9 over n over h to the n to the 4 plus compares with this. I have a bunch of other things here. My initial thinking will be this is likely something that is divergent, just because the dominant term seems to be this 9 to the n, and this is on the top. This is on the top. So I think this is a divergence here. And this is something that I can double check just by doing the biggest number in the denominator and using the divergency test. So remember, the divergency test says that if I have a series an, but the limit when n goes to infinity of an is different from 0, then that implies that the series diverges. So that is the divergency test. Now, I believe that this one is likely going to be divergent just because it has a ratio on it that is bigger than 1. The problem is that it has a lot of other clutter in there. But then if I just do limit when n goes to infinity of 9 to the n plus n to the 4 over a to the n plus 5 to the n, and I just divide everything by a to the n, which is the largest of the denominator. This is going to be 9 over 8 to the n plus n over 4 a to the n, 1 plus 5 over 8 to the n. So notice that this is now giving me ratios. This is 1 plus, and this goes to 0 when n goes to infinity. This goes to 0 when n goes to infinity because a to the n grows faster than n to the 4. But the problem is 9 over 8 to the n, this goes to infinity. So this goes to infinity over 1 or infinity. This is different from 0. And so the series diverges. Does that make sense? So this is critical. One of the critical things that you should always take a look first is, do you think that the limit of the sequence inside of the series is not 0? If that is the case, then likely it's going to be divergent. And you can do it, you can prove it by doing the limit, and you can prove that the limit is different from 0, then it diverges for sure. Now, you don't have necessarily any information if this is 0. If this is 0, you cannot tell either. It can be convergent or divergent. If the limit is 0, you don't have enough information. And just a reminder of that, consider this: 1 over n squared, 1 over n squared. This is divergent, this is convergent. Both of them had limit 0 as this, but in the sequences. So you gotta be careful with that. But if you have that is different from 0, then for sure, you know, yeah, this is divergent. Okay. So divergency test, very important thing to remember. Now let me move to close the session for today to show something else. I should do one example with ratio. And so for ratio, I'm going to use this example here of the series from k equals 1 to k factorial over k factorial square. And I'm just going to use the limit of ak plus 1 over ak. I do absolute value because I want to test immediately for absolute convergency, but there isn't really an alternating piece. So it's not going to matter much. This is just that. And when you do this, that's transformed into the limit when k goes to infinity of 2k plus 1 factorial over k plus 1 factorial square times k factorial squared divided by 2k factorial. Now, the key thing here is that you gotta remember what a factorial is. And in factorial is the multiplication of 1 up to n. And so if you have something like 2n factorial, it can be confusing because this is just really the multiplication of 1, 2 times 3 times n at a certain point times n plus 1, n plus 2, up to 2n. So it continues just going. And so it might be getting even more confusing when you do like 2n plus 1 factorial. Okay? But what you gotta check is that those things are correctly written when you're working here. So for example, this twice k plus 1 factorial, you can just write this as 2k plus 2 factorial. And so when you do that correctly, then you can see, oh, okay, so 2k plus 2 factorial, this is just 2 away from this. I'm gonna have left the term 2k plus 1 and the 2k plus 2, and I'm going to be able to cancel out the 2k factorial. So that's why I have this part left here, 2k plus 2, 2k plus 1. Now, for the k factorial square situation, I have k plus 1 factorial square. And so I can just see that as k factorial times k plus 1 square. And so I can cancel with the 2k factorials that I have right here. And at the end of the day, I'm just going to have 1 over k plus 1 for each of those 2k factorials that I had. And so now I have here 2k plus 2 times 2k plus 1 over k plus 1 square. And then when I do the limit here, that's going to give me 4. Ratio test says that if something is larger than 1, then that's going to be divergent. And so in this case, that is divergent. Another way that I could potentially think of this is you could kind of do this by divergency test, likely just because of the fact that the top is 2k factorial. You know that it's growing larger than the bottom, or you might think so, but it's difficult to tell. It's difficult to tell if this limit of this 2k factorial term over k factorial square it's difficult to know who's going to be larger. If 2k factorial or k factorial square. So that's why we approach it with ratio tests. Okay, any final questions at this point? We're reaching the end of the session. So I just want to very quickly give you time to address any questions that might pop up in the last second. I will encourage you to take a look at this full solutions. I have, like I mentioned before, I didn't cover the surface area, but the surface area is the same idea with the arc length. You have a couple of exercises that are covering surface area. Here I have some multiple choice question where we're addressing surface areas examples. And of course, you can, for the exam, you can also use the extra practices that are available on the WebAssign for the exam. Remember, the exam is in WebAssign, so practicing in there is also a very good way of getting ready for the exam. So now I give you back the floor to you. Any particular questions? Nothing so far. Give me a thumbs up if it's all good. Then. All right. So okay. So thank you for coming to this preparation session. But remember, a lot of this writes in your own work, your own doubts. So just make sure to go back and check. This is going to be in test preparation 2. There's going to be a module for this called test preparation 2. So make sure to check that out and your preparation on the weekend, okay? But otherwise, just have a good day.